Team 7, and we are currently working on the user subtle-G switch. And today we'll give you a presentation on accelerometers. Today I'm going to introduce you a few terms, G, and go over the history of the accelerometer. And then DJ will go over the multiple types of accelerometers and how they work. And then Tom will go into what are MEMS. And then Zhao will give us the differences in digital and analog. And then Frank will close us out with applications and a conclusion. First, for a frame of reference, what is a G? 1 G is acceleration with reference to Earth's gravity as 9.81 meters per second squared. And some different references for that are there are vertical and horizontal Gs that we experience. And here's just some various reference Gs. And some things to note are that roller coasters actually are very close to the limits of loss of consciousness in most humans. And in free fall, we actually experience 0 Gs. Just that's also considered like weightlessness, is we're not actually accelerating, and that could be considered orbit of satellites and different things like that. There are also, you'll notice a space shuttle launch is actually under horizontal Gs, because while the astronauts are in the launch position, they're actually sitting horizontally with their chairs rotated back. And the reason that you'll notice also that 10 Gs is quite a bit more than 8 Gs, which is the limit of sustained human tolerance, and that's just, the astronauts are just trained further, obviously, with centrifuges and different things like that. And lastly, there's also rotational acceleration that can be measured in roll, pitch, and yaw. A brief little history of accelerometer. The very first accelerometer was created in 1923, and it was credited to McCollum and Peters. And it is a resistance bridge type. And how it works, or a little bit of what it is it's an E-shaped frame with 20 to 50 carbon rings, and it works as a half bridge between the top and the center. And it was only commercialized 5 years later in 1927 through Southrec, which was later BSL Electronics. And it wasn't very widely popular as it was fairly expensive, and the use of these kinds of things weren't very widely used yet, only used in bridges and some aircrafts. And then later they came out with a revision in 1936, and it could actually was 2-axis and could withstand up to 100 G, or measure up to 100 G. And the applications increased not only to just measuring peak acceleration, but it was used in measuring vibrations in underground pipes, different steam pipes. And its price, I couldn't find a price for the original, but the price for the upgrade was $420, and that's over $6,000 in today's terms. And I'll hand it off to DJ, and he'll go over the different types of accelerometers.
Okay. Hi everybody, my name is David Eaton. I'm going to be talking about the different types of accelerometers and how they work. Doing some research, I found out that there's probably about 20 to 30 different types of accelerometers out there. I'm going to go over about 4 or 5 of the main ones. The first one is your capacitive accelerometer. That basically just consists of a mass, a spring, 2 fixed capacitor plates, and 1 dynamic plate. And the sensing unit of this is those capacitor plates. And basically, as the force is applied to the mass of the accelerometer, this dynamic capacitive plate moves. Basically, that creates a differential in capacitance across these 2 plates. That difference in capacitance also creates a difference in voltage. That voltage is picked up through a summing amplifier, which amplifies the signal and creates it into a voltage. So basically, if you were to think of it as this thing not moving at all right now, it basically has the same difference across both capacitive plates. So it outputs about 1.4 volts generally, but as you give it a force and the dynamic plate moves, it creates a difference in the voltage, and the voltage will either go up or down, and according to that, you basically get an acceleration value off of it. And the next type is a piezoelectric accelerometer. That's there's a group earlier that talked about the piezoelectrics. It's kind of piggybacking off that idea. Basically, you have a mass right here, and you have a piezoelectric material. And as force is applied, that mass comes down and compresses onto that piezoelectric, and it creates a voltage change outputting from the piezoelectric. And basically that change in voltage also represents the change in acceleration of the device. This right here is a little more in detailed drawing of what an actual piezoelectric looks like. As you can tell, it only really works in one axis, the same as the capacitive accelerometer. So in order to measure all three axes, you need three of these all oriented in different positions to catch a 3D movement. Piezoresistive, it's basically the same idea as the piezoelectric, but instead of measuring voltage coming off of this element, you're measuring the resistance. So basically, as a force is applied to this mass, you get a change in this resistor value right here, and so it flexes and changes resistance value. This resistance is placed inside of a Wheatstone bridge, and basically as this changes, the output from the Wheatstone bridge changes also, and you get that change in voltage, which correlates to a change in acceleration. The Hall effect accelerometer, I thought this one was kind of interesting. It's basically just a semiconductor that you apply a DC voltage to, and as this magnet is far away, the field's not affecting this semiconductor, the current flows really easily through this loop, and not much goes to this side loop here, the Hall voltage loop. But as the magnet becomes closer and closer to the material, its field impacts this flow, and basically causes electrons to flow through this outer loop instead. Basically, as this loop gets higher and higher, basically the magnet's becoming closer and closer. That just correlates to an acceleration of the object also. And then the last one that was also pretty interesting is actually the heat transfer accelerometer. Basically, this is a outlooking image of this. This is just a heat source right here with 4 thermal resistors. And basically, as the object is sitting on a table, not moving, you're going to get an equal value through all 4 of those resistors, basically showing that there's no movement, there's no tilt, there's no G's really affecting the object. But as you tilt the object, the resistors become higher, like this one becomes higher than the other 2 down here, and it basically correlates to the fact that it's tilting, and you can represent that this thing's moving or tilting in a different direction from those resistors. I'll now pass it on to Tom. He's going to talk about MEMS.
Thanks, Dave. Again, my name is Tom Letter. I'll be talking to you about MEMS technology. And so MEMS basically stands for Micro Electromechanical Systems. And all they are is very, very, very small machines on the order of a micron to a few millimeters, I'll say. And they're made in the same way that ICs are, in that you have some substrate and you just place semiconductor material upon that substrate to get certain traces. So we use these to create transducers, transducers that can take in inputs and generate outputs like a motor or a microphone or a speaker or something like that. Like DJ was saying, there's capacitive accelerometers, and so here's actually a close-up of a capacitive accelerometer in MEMS terms. You have these fixed plates here, and then the movable plates. And so that movable plate will move in between the 2 fixed plates and create a difference in voltage, or a difference in capacitance, which correlates to the difference in voltage. So how do we make MEMS? First, if you want to make MEMS, you have to understand there's a couple basic processes. There's etching, which is where you have some substrate and you place a mask upon that. The mask will keep any material that you want for traces, basically, and then you apply either a chemical solvent or some other method of removal that removes the rest of the material that's not masked. Excuse me. So there's also lithography, where you place a mask upon the substrate, and that mask just shields this photosensitive material. And then when light comes down upon the material, anything that's not covered by the mask just gets wiped away, basically. The last type of basic process is deposition, where you have some target material and then you have your substrate, and you use some process either with chemicals, some kind of chemical solvent, or some evaporation techniques that will take material from your target and move it to your substrate, getting the patterns that you want. These basic processes are then used in different manufacturing processes. So the first process that was developed for MEMS was bulk manufacturing, in that with bulk you have a substrate and you basically use one of these techniques to bore the pattern that you want out of the substrate itself. There's also surface manufacturing, wherein, as you can see down here, you start out with a substrate and then you basically apply an oxide mold to it, and you're going to fill that mold with polysilicon material, as you can see here. And then you're going to use some kind of solvent to remove the oxide, and then you're left with like a cantilever on here. This cantilever will be used for some springy mechanism. Now, the most recent development we've had in manufacturing processes for MEMS is the high aspect ratio. And that basically combines the best features of bulk and surface manufacturing and creates something like this gear here. And so it combines bulk and surface manufacturing in that it bores into the substrate, but it also takes these cone-like top layer properties that surface manufacturing uses and creates something that has really high accuracy, really deep, detailed objects. So how do we use MEMS? Well, like I said before, we use them for transducers to sense and actuate stuff. As you can see here, here's a picture of actually a MEMS motor. These pads will supply some kind of potential that will rotate this tiny little gear. So this will be advantageous when, say, you have an application where you can't really use a big induction motor or synchronous motor, or you don't want to mess with the magnetic fields generated by those coils. So then you can use an electrostatic motor, such as this one. There's also pumps and fluid control, which could use the same technology. You could have like a micro valve that could take a tiny, tiny sample of somebody's blood. Accelerometers use them, like DJ was saying, and basically the accelerometer, the MMA 7331, which is in our project, uses this technology. Gyroscopes, they're basically in Nintendo Wiimotes. There's a gyroscope in there, and these just detect like pitch and yaw. There's also, probably the most interesting example was, so if you use MEMS, like a ton of MEMS, that are on the microscopic scale, you can actually get macroscopic effects in the way that they use these for microflaps on the edge of a plane wing and actually steer the plane just with these tiny little micro machines. So I thought that was pretty interesting. But yeah, so now I'm going to hand it off to Xiao, who's going to talk about digital versus analog.
Morning class, I'm Xiao. I'm going to go over the different outputs for accelerometers, digital analog. So one of the most important criteria is when you're choosing an accelerometer is its output, whether it's analog or digital. And they both have their strengths and weaknesses. And I'll go over briefly of both and a little into the digital communication protocols. So for analog outputs, it's pretty much just a continuous voltage that is proportional to the acceleration. So for example, if it's at 1G or 0G, it'll be outputting 1.4 volts. And if it's at 1G, it'll go somewhere like 1.5, 1.6, depending on how the accelerometer is scaled. And because it's an analog output, there's going to be offsets and filtrations and amplification needed to interface with the microcontroller. One of the best things about analog accelerometers is its easy interface with the microcontrollers. The one we're using for our project, MSP430, has the read ADC command, which literally takes the input and converts it to a digital value, which we can use for coding. So that's really good. And the resolution is completely dependent on the microcontroller and not the accelerometer. So for digital outputs, it uses the pulse width modulation to produce the signal. So if it's at 50% duty cycle, it's at 1G. If it's anything above 50%, it's at, or if it's at 50, it's at 0G. If it's anything above, it's at higher than 0G. If it's below 50% duty cycle, it's less than 0G. And it's very practical with microcontrollers that take digital input. And because we need to calculate the duty cycle, it does require timing resources of the microcontroller to measure the duty cycle and some division calculations to do that as well. And it requires some digital communication protocols such as I2C and SPI, which I'll go over the next couple slides. So SPI stands for Serial Peripheral Interface. It's a synchronous data link developed by Motorola, and it's very, very simple. It's like what an ideal electrical engineer would do. It consists of 4 signals. The first, the synchronous clock, which is the clock from the master. In this case, master is the microcontroller, and the slave is the accelerometer. So the clock is from the master, and there's the MOSI, which is master out, signal, slave in, then master in, slave out, and then there's the slave select. So pretty much what happens is, as soon as the slave select signal is put low, the communication between the master and the slave begins, and as soon as it's put high again, the communication stops. There's a bunch of modes of communication here that I didn't mention up here, but there's 4 of them, and that pretty much says how this is functioning. So as you can see, it's very simple. It's low cost, and then there's no pull-up resistors required, so it's less power consumption than I2C, which I'll go over next. So I2C stands for Inter-Integrated Circuit. It's unlike SPI, it only has 2 signal lines. They're bidirectional, the SDA and the SCL. SDA stands for synchronous data and synchronous clock. So what happens is that when the master wants to communicate with the slave, the packet it sends has the address selected. So for example, the master first starts with the start bit telling the accelerometer, hey, I'm about to send an address, so please pay attention. So that start bit is followed by the 7-bit address and a read and write command, depending on what you want to do. So what happens is the slave compares his own address to the address sent by the master, and if it is the same, then it sends an acknowledge bit back to the master. If it's not the same, it just waits for the stop bit. So when the master receives the acknowledgement bit, it sends the 8-packet data with acknowledgement saying that, you know, I'm done. So as soon as that happens, it sends one more stop bit to everybody, to all the slaves, accelerometers, and pretty much it just starts again and waits for another start bit. So one thing to know about I2C is that it does only have 3 modes of operation at 100 kilobytes, 400 kilobytes, and 3.4 megabytes. So there is limitation on the speed, and it's definitely more complex to set up than SPI. So a couple pros and cons. As you can see, I2C uses only 2 lines instead of 4 for SPI, so it's ideal for large networks because it requires only 2 lines. And SPI, however, is definitely ideal for high-speed communication because there's no limit to its speed. And it's usually often used over 10 megabytes when people use them. So I guess to summarize, I2C is more complex to set up because of the addressing and all that, but it definitely has more advanced features such as multi-master conflict handling and addressing management, but that does lack in performance when compared to SPI. So obviously SPI is definitely simple and easy to understand and offers a fast data transfer rate with a high rate of freedom. It's usually used to communicate between ICs and microcontrollers. With that, I'm going to hand it off to Frank. We'll talk about applications.
Thank you, Shao. My name is Frank, and I'll quickly go over some applications that accelerometers are used in. A big one is consumer electronics, and this is because it's very good at detecting changes in motion, changing in orientation, and that's critical for things like iPads, tablets, Wiimotes even. And it also it's used in cameras to stabilize your pictures so it can compensate for the movement of your hands. And another application is it's in laptops. So when the laptop is falling from a desk, it can sense that and protect its data by parking its heads of the hard drive. But there's a whole world of applications, really. So I'll just go over a bunch. One is in navigation. It can be used to calculate altitude, speed, distance, direction, things like that. It's becoming used in medical fields, like Nike has a big campaign to use it for monitoring exercise for the user's information and for doctors' information. It's improving the success rate in surgeries, including hip replacements and even like heart bypass surgery. There are many bio applications for it. Structural, it can more accurately measure the loads in a large building. And also, of course, industrial, which brings us to our design, which is the user-settle G-switch. And the primary goal of that is to shut down machinery if there's excessive vibrations. And it can do that very accurately, very well. And it also can do a lot of other things. G-switches are used for transportation monitoring for high expensive cargo, and also can do seismic activity warning, earthquake preparation and such. But today we went over accelerometers, and lots of acceleration, I guess. But Sean went over the history of accelerometers. David Eaton did the types of accelerometers. Tom did MEMS technology, and Xiao did digital versus analog comparisons. I went over the applications. Thank you from Team 7, and are there any questions? Thanks again.